Understanding how substances handle energy is essential in thermodynamics. This topic focuses on two key areas: thermodynamic properties. Internal energy, enthalpy, and specific heats describes how substances store and respond to the heat. These properties helps us calculate energy changes during heating, cooling, and phase transitions. Also, the first law of thermodynamics, this fundamental law states that energy cannot be created or destroyed. This only transferred or converted. When a closed system or control mass undergoes a cyclic process, its internal energy returns to the original value, and all the heat added is converted to work. So together, these concepts form the foundation for analyzing engines, heating systems, refrigeration, and many natural processes. We will now proceed with the main topic. So, what is enthalpy and internal energy? When we say enthalpy, it is the heat energy that is being absorbed or involved during progression of a chemical reaction. The enthalpy is given the symbol H that indicates the amount of energy. The change of enthalpy is given as the delta H, where the symbol delta indicates the change of enthalpy. The enthalpy is also given in joules or kilojoules. We can also say that enthalpy is the sum of the internal energy of a system. This is because the internal energy is changed during a chemical reaction, and this change is measured as the enthalpy. The enthalpy also is a process that occurs at a constant pressure, can be given as H equals U plus PV, where H is the enthalpy, U is the sum of the internal energy, P is the pressure of the system, V is the volume of the system. So therefore, enthalpy is actually the sum of internal energy and the energy required to maintain the volume of a system at a given pressure. So, the term PV indicates the work that has to be done on the environment in order to make space for the system. The enthalpy change indicates whether a particular reaction is endothermic or exothermic reaction. If the value of delta H is a positive value, then the reaction is endothermic. That means that energy should be given to the system for outside for the reaction to occur. But if the delta H is a negative value, it indicates that the reaction releases energy to the outside. Furthermore, enthalpy change occurs in the change of phase or state of substances. For example, if a solid is converted to its liquid form, enthalpy is changed. This is called the heat of fusion. When a liquid is converted to the gaseous form, the enthalpy change is called the heat of vaporization. And we have here example of enthalpy. Example, boiling water. When water boils at the atmospheric pressure, it absorbs heat without a temperature change. This energy increases the enthalpy as the water turns to steam. And now let's proceed to the internal energy. When we say internal energy, it is the system that sum up of potential energy and kinetic energy of that system. Potential energy is the stored energy, and kinetic energy is the energy generated due to the motion of molecules. The internal energy is given by the symbol U, and the change in the internal energy is given as delta U. The change in internal energy at a constant pressure is equal to the enthalpy change in the system. The change in the internal energy can be occur in two ways. One is due to the heat transfer. The system can absorb heat from outside or can release heat to the surroundings. But both ways can cause the internal energy of the system to be changed. The other way is doing work. Therefore, the change in internal energy can be given as delta U equals Q plus W, where delta U is the change in the internal energy, Q is the heat transferred, W is the work done on or by the system. However, an isolated system cannot have a term delta U because internal energy is constant and the energy transfer is zero and no work is done. When the value for delta U is positive, it indicates that the system absorbs heat from the outside and work is done on the system. When the delta U is negative value, then the system releases heat and work is done by the system. However, internal energy can exist as potential energy or kinetic energy, but as not as heat or work. This is because heat and work only exist when the system undergoes challenges or changes. Here, example of internal energy. So, car engine fuel combustion increases the temperature and the internal energy of the gas, which pushes the piston to do work. So to sum up, enthalpy is related to the systems that are in contact with the surrounding, and the internal energy is the total energy that a particular system is composed of. However, the change in enthalpy and change in internal energy are very important in determining the type and the nature of the chemical reactions that are going on in a system. Therefore, it is important to clearly understand the differences between enthalpy and internal energy.
Good morning everyone, this is Ken Jasper B, and today we are going to continue the report of Ms. Ramperas, the other thermodynamic properties, the specific heats. So what it means when we say specific heats? Specific heats, it is the amount of heat required to raise the temperature of a unit mass of a substance by 1 degree.
For example, while specific heat for both a large block of iron and a small iron nail is the same, heat capacity will differ as a large block of iron will need more heat to raise the temperature by 1 degree, while the small iron nail would need relatively less heat to achieve the same temperature increase.
Specific heats at constant volume, C subscript B, is the heat capacity when the volume is held constant. C subscript B is the amount of heat required to raise the temperature of a unit mass of a substance while keeping the volume constant. Under constant volume, no boundary work is done because the system does not expand or contract. All the added heat goes into increasing the internal energy of the substance. This is especially relevant in closed systems or control masses where expansion is restricted. Specific heat at constant pressure, C subscript P, it is the heat capacity when the pressure is held constant. C subscript to P is the amount of heat required to raise the temperature of a unit mass of a substance while keeping the pressure constant. Under constant pressure, part of the heat energy goes into doing work to expand the system, and part goes into increasing internal energy. C subscript to P is typically greater than C subscript to B because it is